Hello? I just screwed up my recording. Oops. Sorry, I accidentally hit a button. Hello and welcome to Chapter 5, where we're going to talk about discrete probability distributions. Just to give you some quick reminders, discrete means to cut or to cut apart. So these were the ones that we can count. I'm going to review that in a minute also, so if that was like a short explanation, hopefully you enjoyed it. And just as another reminder, and this one isn't later, probability distributions are very specific. So when it comes to making a distribution, we're really looking for two things. Does it describe all the outcomes of my variable? And does it describe how often they occur? So it really does two things for you. What are the possible values and which ones are the most frequent or less frequent? So what's different about the distributions we're going to do today and what we've done in the last chapter is that when we think about distributions, we're using probability to describe how frequently, as opposed to just counts or frequencies. So we're relying on probability to say how often for those. So today we're going to be covering how to do some expectations, because that's a fun word, for discrete probability distributions and discrete random variables. And then we're also going to look at a specific type of discrete random variable and discrete distribution called the binomial distribution. Now you'll notice I've crossed out outcome number 3, which is the Poisson and the hypergeometric. These ones really don't show up as much, and we are not required to cover them, so we will not be doing them. If you would like to look over them on your own, you may use your textbook to do so, and there are some videos in our video library for the textbook on my stat lab to view those as well. So we really have two outcomes today, but you know, getting to understand the binomial can be kind of difficult, so this will take a little bit for us to understand, and we're going to do it by hand for the lessons today. However, you'll notice that we have a mini tab this week, and the mini tab will go over how to do some of the calculating on mini tab. So if you don't like the by hand calculations, focus more on understanding the setup, because you'll need that for mini tab. Oh, and when the situation occurs as well. All right, so first up, random variable. Just a reminder, this is a variable where we don't know the outcome of what it's going to be ahead of time. That's what makes it random. And everything here is based on chance, random chance, of course, hence the name random. And so discrete, we've already talked about. Discrete means to cut from Latin, or in our case, it's going to be a finite sequence that you can count. What that means is I only can have whole possibilities. I can't have halves or anything like that. So for instance, time is not discrete because you can cut it into smaller pieces, like instead of using hours, minutes, and seconds, and even microminutes and, well, not microminutes, microseconds if you're maybe somebody who's swimming in the Olympics and want to keep track of your times and that kind of stuff. Those are actually ones that feel more continuous. Time is definitely continuous. It has an uncountable infinite number of possibilities or possible number values. So when we talk about continuous, it feels like an infinite number of possibilities that we don't know ahead of time. Discrete, because we can count them, usually are a little bit easier to describe. And we're going to look at ones that are finite in particular, although it can also be infinite as well. There will be a couple infinite ones that I do in the mini tab lesson. Alrighty, so here's some more examples of discrete random variables. The first groupings are ones that are more possibly infinite in nature, so we can only get so many, but we don't know how many we're going to get ahead of time. So number of complaints per day, number of TVs in a household, number of rings a telephone before it answers. Obviously that's going to feel like infinity because nobody talks on the phone nowadays. And then we're also going to focus more on, for the binomial in particular, stuff that has only two possible outcomes. Yes or no, game results being won or lost. You either have this characteristic or you don't. So like you either have brown hair or you do not. You either are self-employed or you're not. There's only two outcomes, and those are going to be ones that specifically apply to the geometric when we look at it. Alrighty, so here's an example of a discrete random variable, and you'll notice I have a table down below. This is I wish I could count that out. I'm getting tongue-tied. This down below is what we would call a distribution. So this is what we were talking about where I said, oh, number of values possible, 1, 2, 3, 4, 5, 6. And then I'm using probability for my frequency over here on the right column. So you notice each of them has a certain amount that they have a likelihood of doing, with being 3 having the most often since it's the largest percentage or the largest probability in this case. And notice, thanks to the law of total probability, I know that this is all of my possible outcomes because it sums to 1, which we also think of as 100%. So these are from a La Quinta and from their show homes. Sorry, not a La Quinta, California. That was awesome. I probably should record this slide, but my voice isn't good enough for me to risk it today. Good times. I don't know what I'm doing now. Anyway, so this is an example of a discrete probability distribution. That's what they look like. So we've seen stuff like this before, back when we were doing frequency distributions. Under certain conditions, if the outcomes were random, hey, it was a discrete random variable we were looking at. So you didn't know the name of it back then, but you still knew what it was. So this harkens all the way back to chapter 2 when we organize things in tables. Here is a graph of the probability distribution. We ironically also call the histograms of these a probability distribution as well. So it's interesting because these are very different looking, but at the same time they're given the same name because they accomplish the same task. They tell me what values it takes on and how often it takes on those values. So keep that in mind. These are actually just different ways of representing the same thing because it accomplishes those two tasks. All right, so here's a more interesting example for that. So here's two discrete probability distributions that have totally different looks to them. So don't assume they're always going to look the same because they have a wide variety of possibilities. So for the one on the left, it's one that has only 3 outcomes, and then the one on the right has 21 possible outcomes. And keep in mind, yes, even though they are countable, they can be infinite looking. However, the infinite looking ones usually have some of the properties that this 21 one has, where it has one tail that kind of trails off and starts to get so small it's really hard to tell what the probabilities are because they get so teeny and small that they almost look like nothing. That doesn't mean they're not there, they just are really tiny. Alrighty. So, expected value. One of the big mistakes people make with expected values, they think it's something different from the mean. It is not. It is just the way we represent the mean in a discrete probability distribution. So what that means is this is the value we expect to see, or the most typical value, and if you remember, that's how we interpret the mean. So often, textbooks, instead of writing expected value, will also write the fancy M for mean as well for this, because it is the same idea. So be careful, this is the value you expect to see. So how this is calculated is it's based on probability times the value itself, and then we add them all up together. So if you remember back to when we would calculate a mean normally, or when we had a list of data, so if we just had like the average age that we were looking to calculate of everybody in our class, we'd just gather all the ages for all of our individuals, add them all up, and divide by n. So what you were doing there is you were dividing assuming that everybody had equal weight. And if you remember anything about the weighted mean, that was back in chapter 2, which you may or may not have looked at. No, wait, chapter 3, sorry, I almost said the wrong one. This is the same idea, but here your weights are based on probability, and since all of your probabilities have to add up to 1, the weight you're dividing by is 1, and that's where this formula comes from, which is kind of interesting. So keep in mind as you look at this, probability has an effect because we want events that are more probable to show up more often, if that makes sense. It's kind of like you think about winning the lottery. On average, you're going to lose money because the probability that you are going to win is very small, but the probability of you going to lose is very large. And what happens is you'll have the value that you spent on the ticket versus the value you might win, and overall you should expect to lose money on average because that's how the lottery makes money, in case you didn't know that. Good times. It's also a good point to bring out when it comes to probabilities. Just because there are 2 outcomes doesn't mean they are equally weighted or equally probable. So be careful with that. All right. So going back to the number of bedrooms and home sales. So this is that La Quinta, California data again. What I've done here is I've done the first step, which is I multiply the x value times the probability, and that appears right here. And then you're going to do this for each and every x value. So you notice that if you have 1, 2, 3, 4, 5, 6 here, you're going to end up with 6 of them that you do, and then you'll add them all up. That's what the sum means, and that's how you get the expected value. So you should expect, on average, a home in La Quinta, California to have 2.85 bedrooms. Yeah, this is the mean of the probability distribution. A while ago, back in the early 90s, people used to joke about how on average you were supposed to have 2.3 children. Same idea. Remember, your average doesn't have to be a value that's in your distribution. It just represents what's typical or what's going to happen on average, or what you expect to see. Different, right? All right. Now, let's look at a rather different example of this. So this is a little bit more like what I was talking about with the lottery, but a little bit more complicated. So suppose you're going to play a game of chance and you have to pay $3 to play. So keep in mind, you're going to think of your paying in money as a negative, or values you're going to lose. When you have 6-sided dice and you have payout equal to $1 times the number of values that could possibly come up on the dice. So as you're looking on this graph, you might be a little surprised on what I've got for my table. So be careful on what you're looking at here. Let me explain this a little bit better. So over here I've got my probabilities. Each of my values are equal here because you have a 1 in 6 chance of getting any one of the values. This first value here is what would happen if I rolled a 1, because if I roll a 1, I win $1, but I paid 3. So essentially this is a negative $2, and that's why it's in red in parentheses, because that's the standard notation for a negative used by accounting. If you don't like that, go ahead and just throw a negative sign out in front of these suckers, and that'll take care of that, right? Good times. So the value you see me just now writing a negative right here, this is what would happen if you rolled a 2. You'd get $2, but you paid 3 to play the game, so you only really netted yourself a negative $1 there. Yep. And then similarly, here's what would happen if you roll a 3. Since you paid $3 to play the game, you end up with a net value of 0. I actually should have changed this to a 0 rather than a line. I was trying to use the notation accountants use to make this a little bit more relatable. I don't know if that worked or not. 0. Good times. And then here's the ones where you would win something. So 4 minus the $3 you take to play gives you $1. 5 minus the $3 it takes for you to play, you win $2. And then 6 minus the $3 you take to play, you win $3. So then what we do next is we take and we multiply these two values together and we get x times p. You do that 6 times, you fill out this rest of this table, and then you add them all up to get the expected value. So this is actually a good game to play because you'll notice overall I win something positive. That means if I played the game a long number or frequent number of times, on average per play, I would win 50 cents. Most of the modern games that are played in casinos have a negative expected value, which means in the long run, you're going to lose money. So, not to discourage you from gambling or encourage you from doing so, but just, be a little bit aware of what you should expect to see on average if you play a large number of times. Yep. Or as they like to say, the house always wins. All right. So if we can do a mean, we should be able to do a spread. Here's what the standard deviation looks like, or the amount of dispersion, or the measure of variation for your data. It's the following. So this is a little bit scarier. I don't want you to be afraid of this because it follows the exact same formulation that we've seen with the standard deviation before. If you remember, standard deviation for a single variable, not a random variable, so just a single value of quantitative data, was the square root of the sum of the x minus the mean squared, oops, that looks horrible. Let's make this a little bigger, divided by n minus 1. I'm using capital N for population here. So how does this look different? Well, hopefully you see the inside parts of the sum look very similar. Like there's my sum, there's my root. Okay, I see that. There's a square, got that stuff. X minus my mean. Oh, remember expected value is the mean, so there's x minus the mean. That looks the same. And then you'll notice there's p, probability, instead of 1 over n. And that's what it's essentially replacing. The 1 over n assumes everybody's equally likely. Here we're using probability to give it weight so that things that happen more often show up more often because, well, they happen more often. They're more likely to occur. Here's an example of us doing the same thing for the La Quinta example. So here I've already got the mean, so we did that earlier. So I just kind of stole that. And then right at this step, we're doing the values minus the mean. So I'm taking each of these values, 1, and subtracting 2.85, and that gives me negative 1.85. 2 minus 2.85 gives me negative 0.85, and so on and so forth. Now I'm doing a lot of rounding in here, which is going to introduce some error. So be careful with your rounding. I know I did 2 places for this, for the mean. So when I squared, I did 4 places because that should increase by a factor of 2. Oh no, a factor of squares. So if I did 2 places, I should do 4. Then I multiplied by the probability. Yay! So at this step, we're multiplying the squares by the probability, getting the following values, adding them all up. Notice the last thing I need to do is take a square root of those, so that's where that value comes from. You take the square root and you get about 1, which makes sense when you look at the table. Earlier we said the mean was about 3. Yeah, 2.8-ish. And then if you look about 1 around that, you get most of the data. So about 1 around it would be down to 2 and up to 4. And that's pretty much all the data, because the only thing it's really missing in here is 1 and 5 and 6, and those have a probability of about 20%, which is not all of your data. So most of your data is close to the mean. This makes sense as a spread for this distribution and for all distributions that are discrete random variables. Alrighty, let's go back to the dice game and we'll play the same game. So I've got my payoff amounts and my probability on here again. I've included the mean that we did earlier of 50 cents. So we're just going to take everything, each of our values here in the x values, subtract the mean to each of those, and you get the following. So your negatives become even more negative. That's fun. But notice that when you square them, they all become positive, because that's what squaring does. It also makes things bigger, which is why we got a root later. Then we're going to take each of those, so each value here, multiply by the probability, woohoo, and that gives you each of the values in this last column. So that's where all of those come from. And then when you add them all up, you get the sum. Then the last thing you have to do is take that sum and square root it. And that gives you $1.71. So that's actually quite a big spread. What that tells me is, although my average is 50 cents, I can have a spread of about 1.7 or $1.70. So it might be I get up to about a little over $2 in winning, or I could go down to losing about $1.50. So it's an okay game. It's not great, which, you know, there's that. The fact that you have an average expectation of something positive is actually really good. So this is probably some kind of kids' carnival game where they didn't want the kids to feel bad about losing something, or losing a lot. Let's take a look at another example. So this is a fairly typical experiment for us to look at when it comes to counting things. So suppose you take a fair coin and you toss it 2 times. This hopefully looks a little bit familiar compared to our discussion board of last week. I wonder if I had that in mind. Hint, hint, wink, wink, I don't know. Be aware that the variable I'm going to keep track of here is the number of heads the distribution shows, which means I don't care about tails, I care about heads. So when we have something like tails shows up, hey, that's going to be a 0 for my random variable because I'm only counting heads here. How many heads are there? None in that outcome. So you'll notice I've listed all the possible outcomes from this experiment, the following, and that the possibility of getting a 1 actually shows up in 2 different ways. Be careful, tails head is not the same as heads tails. This is one of the common mistakes people will make with tossing coins and other examples. Just because they have the same outcome, you have to be careful. Does order matter or not? Most of the time, order does matter, so be careful. Don't assume it doesn't matter if you're not sure. And since this has 2 possible outcomes, it has a higher probability than the rest, which is kind of interesting. You can repeat this with other things that are not fair if you want to get some other interesting probability distributions. So now let's take that and find the mean. So here this is fairly simple, so I've written out the equations in long form. Feel free to enjoy that. So for the first one, to do the expectation, we multiply, 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 and then add those 3 together. So you see them here, here, and here. And you'll notice that the average is a 1, not a shocker. It falls dead in the center. This is a very balanced distribution. If you graphed it, you'd notice it kind of looks like this. 0, 1, 2, because we're counting heads. It's very even and very symmetric, so it's not too shocking that the mean shows up nice and in the middle. Anyway, let's take a look at the spread. So just like before, I'm going to take the mean of 1 and subtract it from each of my values, square it, and then multiply by their probability. So that's those guys as the probabilities. And then if you do all that, you get a half, which when you take the square root, you get some, well, this is a square root of 2. Or sorry, square root of 2 over 2, in case you did trigonometry. So it's about 0.7, which is interesting because if you go 0.7 above 1, you don't quite reach 2, and 0.7 below 1, you don't quite reach 0. So you really only get half the distribution straight ways around the mean, which is interesting, but seems reasonable for a spread. All right, let's look at some investments. So as you look at these 3, maybe take a minute and pause the video and think about which one would you like to do and why. I'm going to pause for a second too. So with this first question, I've tried to give you a hint. Do you prefer 1 or do you prefer 2? Why? So looking at number 1, I'm hoping you notice everything's equally weighted. They each have a 1/4 chance of being selected. And then with number 2, the middle two are better. So myself personally, I would prefer investment number 2 because I have a better chance at hitting the middle values. Now, you might be a little bit less conservative than I am and say, hey, I want a higher shot at that $50 because it's more. So you might pick the first investment. Now, and looking at these two, I bet their averages are different because this is more weighted towards the middle with the 0.3s over the 0.2s, or the 30% over the 20%. So obviously investment 2 is going to have a higher expected value. Now, in looking at their standard deviations, I'm betting, since these values aren't too far off each other, only about $10 each, same over here, and these probabilities aren't that different, we're only varying by about 5% into investment 2, their spreads aren't going to be that different. But their expected values will be different, and the fact that this one, investment number 1, will probably actually be bigger because it's got more values weighted towards the middle 2 values. Now, let's look at investment number 3. Investment number 3, I like to point out, yes, it does have some more probability towards those middle values, but those middle values are also very different from the value distribution you see in 1 and 2. Notice the middle 2 are $10 and $30, whereas this one goes up to $40 in the middle 2. But then when you look at it, you could possibly have a payoff as low as $5 or as high as $100. However, that $100 only happens about 10% of the time. So the mean for this one is probably much smaller than the other two, since there's a large percentage or a 20% chance, which is the same as investment 2's chance, and close to investment 1's chance for the lowest value. However, its lowest value is much smaller by a factor of 4, or a fourth, than the other two. So that alone, along with the small chance of getting something really large, is going to create a greater variation here, or a higher standard deviation. And it's going to have a lower mean because of that. So it's going to get dragged towards this extreme value that has a larger probability in comparison to its extreme outlier on the other end that's much larger, but has a smaller probability. Now, if you're a risky investor, investment 3 is probably more your bag, man. I would tend to prefer something that looks more like investment number 2 for the reasons I've described. So again, as you look at each of these, investment number 2 is going to have the largest mean. Investment 1 will be close to it, but not quite the same. And then investment 3 will have the smallest of the three of them. When it comes to standard deviation or variation or possibility of differences, the greatest variation is going to occur in investment number 3, followed by investment number 1, and then lastly investment number 2 will be the smallest standard deviation. So if you think about it that way, is variation being represented by standard deviation or change or range of crazy things happening, investment number 2 I would say is the most stable. It produces the most on average as well. So I would choose investment number 2. But if you want to be risky and crazy, go for number 3. Anyway, so here's a breakdown of the exact calculations for each of those. I'm going to go through these a little bit fast. So as you can see, the expectation for 1 is only $35. For number 2, it's going to be $40, so it's going to be higher. But the spread for this one is $11.18. The other one, the investment number 2, will be $18.83. And we'll see that number 3 actually has a mean of $26 and a standard deviation of $26.81 or 82 cents. 81 cents, sorry, I had to think for a minute. So, taking a look at number 2, we see that, oh, my calculations were off with number 2. Oh, I forgot about cost. I didn't include cost for this one for the standard deviation. Oops. Yeah, so my subtraction was a little off with this one, sorry. Anyway, we see the mean is very close and the standard deviation is a little bit smaller because it is more stable. Again, these two have a higher probability and they're close to the center, so on average, a little bit tighter to the center or less spread about the mean. And then let's look at investment number 3. As you can see, investment number 3 has the smallest return on average or smallest expected value and the greatest spread in that return because its standard deviation is the largest. Yep. All right. Moving on to the binomial. So the binomial only can be used for very specific situations. In particular, you have to have some defined success, thing you're interested in, and know its probability in one trial. And then you want to repeat that process a certain number of times, and you know that number of times ahead of time. So again, a fixed number of identical trials. And the other thing about this is each of your trials need to be independent. The reason we need independence is we want to multiply them as we go along. So if they're independent, we can use the multiplication rule for independence and not have to worry about any overlap. And that's how the binomial looks. So I gave a couple examples of this. You know, you either are self-employed or you're not. You're either brown-haired or you're not. You either have an associate's degree or you don't. It's that kind of stuff you either have or you don't have. You're either left-handed or you aren't left-handed. You either kill all your houseplants or you don't. That might be a terrible example. Sorry. The point is to consistently know whether you've succeeded or not succeeded. And it really depends on what you want to be interested in and what you define to be your success. Okay, the other thing is when you're repeating those processes, it has to be consistent. So my houseplant one's probably not a great example because I very likely doubt the probability for that one is consistent for everyone. However, left-handedness is a great one because in our population, about 10% of people are left-handed, which means that I consistently know the probability that success, or little p as we like to call it, for my trials as I succeed them. So if I randomly pick someone from class, the chances that I get someone who's left-handed is always the same. It's about 10%, since that's something that we know about the population. Anyway, so we're going to use p to represent probability of success. That means that failure is 1 minus p. Remember, 1 representing 100%. Minus the p will give us q. So notice they picked q because it looks like p flipped over because it's the opposite of that. So see how the q looks like it's a flip of p because like it's the opposite. So whatever the probability of success isn't, q is. So again, it's like a light switch. It's either on or it's off. There's no in between. So the doors can't be half open. They have to be opened or closed. It's a strange situation, man, but that's how we get binomials. Hence the name binomial. Because, you know, bi for 2, there's only 2 options. Cool. All right. So when looking at the binomial examples, there's many places where you can see this in the world other than the ones that I've mentioned so far. I've been trying to keep my stuff different so that you can see these examples as well that I had planned for later. So you can either have a product that's acceptable or defective. You can either get a bid or not. You can either say, yes, I will buy it, or no, I won't. Or you can either get an offer or not get an offer when you're applying for jobs. Let's take a look at another example. Now this is going to be a binomial. So a bank believes that 88% of its customers prefer the bank to be closed early on Friday, but be open Saturday morning. So they look at 3 customers that are randomly surveyed, and the binomial distribution will apply here. So the reason you know the distribution will apply is because you have a set number of customers you're going to be asking. This is your set number of trials, is 3. And you have a set probability of what you believe is happening. So that's not going to change. So the success is always 80%. The failure is always 20%. Yep. And then what we're going to do is we're going to count how many customers prefer the option, because that's what we define as our success. So it's important to keep track of what your success might be, because you might be doing something like counting the number of defective items you have. Defective kind of seems like a failure, so make sure you do take the time to maybe do this. What am I counting as my success? Because then it makes keeping track of your random variable much easier and what your probability of success would be. So this would be my little p. And this would be my little q. I'm sorry, my q's look weird. I've never learned how to do them properly. Should it look like this? Ugh, I hate that. It looks like it screwed up 8. All right, anyway. So what are the possibilities? So if we have 3 customers, you need to think about what the sample space would look like. Either have 3 fails in a row, a success, 2 fails, a fail, a success, a fail, a fail, fail, a success. So here I'm counting the number of successes is what I want. And then we think about the number of ways that can happen. 2 successes and how they would be arranged. There's 3 of those because the fail could be in the first position, the middle position, or this. Oh, I said first position, last position. Oops. And then for having 3, then you had to have 3 successes, and there's only 3 options, so 3 in a row. Kind of fun. So as you look at this, it's kind of interesting how you have to count stuff, because here there's 8 different options for 3 selections. So if you had a hard time with this, remember you can do this using the decision trees. So you could do success, fail, success, fail. So that's person number 2. And then person number 3, I'm trying to make this fit. I'm sorry, guys. This is going to get a little messy. Success, fail, success, fail. My screen keeps moving on me. Success, fail. Oh no, this is so not going to fit. Success, fail. So the top of the tree is SSS. Success, fail. Success, fail, success. So I'm just following the trees. So this is success, fail, fail. Success. Oh, wait, fail, success, success. Fail, success, fail. Oh man, this looks like a mess. Anybody who watches this without sound is going to have no idea what I'm doing here. And then failure, failure, failure. Woohoo! And then you can separate these into what you see below. So if you're having difficulty with this, try the tree. It'll make it much easier for you to arrange things. I hope that helped. All right, so then let's take this and arrange it in terms of probability. So remember, our probability of fail is 20%, our probability of success is 80%. So the first option that we had of all 3 being failures, which would be our x equals 0 option, there was only one way it could occur, all bunch of fails, 20% in a row, and that's where this probability comes from. I'm going to do the last one next. So all 3 of them being successful was this last option, only one way it could happen, da-da-da-da-da. And then the other 2, well, they got a little messy. So 2 fails and 1 success is this row. And you'll notice, if you remember anything about probability and how multiplication works, I'm just applying the multiplication rule for all of these. And then hopefully you notice that I have 2 20% and 1 80% in all these. And you remember that multiplication commutes. In case you forgot what the commutative property of multiplication is, that means that 2 times 3 is the same as 3 times 2, or I can do this in any order. So if you want, you could have rewritten this row as there were 3 ways it happened. There were 1 success, 1.8, and then 2 fails. And that would get you the same result, the 0.096. So you're thinking you could do this shorter. You totally could, since they're all going to be the same probabilities. It's just 3 ways it can happen. And that's why we add 3 of them together. So you can see where the 3 comes from. Same thing with this middle row, or the third row, rather, because I already did the bottom. Woohoo! Same idea. There were 3 ways it could happen. I had 2 successes, so that's supposed to be a 2, and then 1 failure, and that will give you the same value. So just some couple ways to write this that are different. I am going to start writing them like what you just saw me write in red, because that's the faster way to do these. So with 3, it's not too bad, but you could see where if I did any more than 3 trials, doing this way is going to be a little bit of a disaster. So what I want to get to is figuring out how many different ways each scenario will happen, hence where this 3 comes from, and then doing that times some values. So this is the probability distribution for the banking example down at the bottom in the table and in the graph. Here I actually prefer the table because when you look at the graph, like that's really hard to see what that value is specifically. And when we do this with Minitab, you'll see me do it a couple different ways as well that goes along with this. All right, so suppose the bank interviews 8 customers rather than 3. Yay! So I just wrote it too hard because that's who I am today. Let's do this using a better method. So we're going to use the actual binomial distribution to do this finally. So the first thing we need is a way to count combinations and count number of events and how they occur. This is where things get a little bit more difficult. So the first thing to notice is that we're using factorials. So factorials are where you multiply stuff by itself and reducing the number that you have until you hit 1. So for instance, 5 factorial would be 5 times 4, because it's 1 less, times 3, times 2, I'm not going to make this fit, times 1. And if you multiply those all together, you get 120. Yep, so that's where this is coming from. This is a little difficult. If this is something that you find confusing, I'm going to show you where this comes from using a different example. So suppose you're playing a game in which there's a 10% chance that you'll win. You decide you're only going to play 5 times and then quit because that's who you are. let's find some probabilities. So we're going to find these following probabilities, and these examples are going to help me lead you to where the combinations come from. You not win any games, you win the first game but lose the final 4 games. You win exactly 1 of the 5 games, you win 2 of the 5 games, you win, oh not 2, sorry, 3 of the 5 games. You win at least 1 game. This one is actually the hardest one to do, but I'm going to show you a sneaky easy way to do this. Okay. So the first thing you might want to notice about this is this will be binomial. I am going to be trying 5 times, because that's how many times I'm going to play. My little p, my probability of success, will be 10%, because that's how likely I am to win. Knowing that, my q is going to be 1 minus 10, which will give me 0.9. And my x is going to be me counting my number of wins. Follow? All right, let's do some calculations with this. So I want to find the probability I do not win any games. So this is the probability that x is 0. So if I'm going to win 0 games, that means I'm going to have a bunch of failures, or 0.9 times 0.9 times 0.9 times 0.9 times 0.9. Do I have 5 of them yet? Yeah, I do. Okay, so notice you could have written this a different way, thinking about in terms of what exponents mean. For those of you who really need to know what this value is before you lose your heads, here it is. I'm going to round that to a 5. We'll do 4 decimal places this time. Now, if you'd have written that out using what we're going to be doing today, you would have written it as I have 0.9 to the 5th. Yeah? But I want you to keep it in mind, if I have 5 wins, that means I had 0 losses. So you also could have included 0.1 to the 0 power. Just as a polite reminder, anything to the 0 power is 1. This comes out the same. Because we're going to start getting into that habit as we go through, to include powers of losses, because we're going to need that to do the binomial. All right, so this next one is actually, oh, it should be B. Whoops. Teacher failure. B. You win the first game but lose the final 4. So this one would be I win the first one and then lose 4. Is it clear where I got the 4 from? Keeping in mind we're going to start using exponent ideas. Now, be careful. Notice I didn't label this with that X notation, because this one is not a binomial. Because when we're dealing with a binomial, we want to have the possibility that I count my number of wins. Here I've given a specific order and way it has to happen. There's not many possibilities of what could happen here. There's only one way this could happen, and that's, the loss first and then a bunch of the win first and then a bunch of losses. I knew I said that wrong. This is not the same as I will win 1 game out of 5. That's what we're going to do next. Okay, let's talk about how winning 1 game out of 5 could work. Now, you could have many ways this happens. So you lose 1, or no, I don't want to do that. I want to win 1 and then lose a bunch. So I could win the first one, I could win the second one, I could win the third one, I could win the 4th one, or I could win, so L is for loss, by the way, the last one. So there's 5 ways that this could happen. So keep in mind, what I'm trying to do here is the probability that I win exactly 1, because X is my number of wins. So I've already seen this as 5 ways this can happen. So you start writing out the probabilities for this. Oh, actually, I should erase that. I've got it in a bad spot. I'm sorry. We'll put it up over here for fun, just to keep it out of the way. I'll use that in a minute. So if I was to write out the probability for this first one, that would be I have a win, 0.1, and then 0.9 to the 4th. That's the one we did first. And this one's a 0.9, a 0.1, and then 3.9s. But because I can reorder things, I can change the order, switch these 2 around. So I can swap the 0.1 and the 0.9. See what I did here? I just switched these 2 around. Oh no, wait, that's the same thing again. It's 0.1 times 0.9 to the 4th. So hopefully you're checking yourself on this, like, okay, yeah, if I can move the losses and wins around because of multiplication, even though this is keeping track of order they're in, I could actually write all of these as 0.1 times 0.9 to the 4th. So if you add them all up, you realize, oh, there's 5 ways this can happen. 0.1, 0.9 to the 4th. Okay, so that didn't seem too bad. And if you calculate this, it's not too bad at all. It's just 5 times you know, the value we got before, which is just a little bit bigger than 32%. Shouldn't say that. It's actually kind of close to 33. I'm going to include one more decimal place here because I don't want to round that when you don't have to. Now, where did that 5 come from? It came from me counting how many different ways this could happen. Yeah, just like we did with the successes and failures earlier. There's another way you can do this. You can use it using that CNR notation I had earlier. So if you remember that one, actually your book uses NCX. If you use the calculator, they use an R here, just so you know. So here what I want to do is I want to show you how this connects. I'm just writing out that formula from earlier because I want to use it in a second, just in case you forgot it. I should have written it on the side so it didn't take up so much space. So here what I want to do is I want to have a situation where I'm looking at 5 trials with 1 success. So what's that going to be following our nose? 5 factorial over, now see x is 1, 1 factorial times 4 factorial. Because 5 minus 1 is 4. So keep in mind 5 minus 1 because that's a 5. And that's a 1. So when you write this out, you'll get 5 times 4 times 3 times 2 times 1. Almost every time I do these, I get tempted to not write the times 1 because it's dumb. 1 factorial is just 1 times, now I'm doing 4 factorial. 4 times 3 times 2 times 1. And you notice there's a bunch of stuff you can get rid of because 1 divided by 1 is silly, 2 divided by 2 is silly, silly, silly. Oh crap, it's 5. Oh no, I wonder if this is connected. Yes, it is, because it's the one that's giving you that value out front. It's counting how many ways this can be done. I didn't label this yet. This is a probability that you have 1 win out of 5, where you don't care what order the 5 occurs in, or sorry, what order the win occurs in. Let's look at a more complicated version of this. I'm going to look at D. Oh, hey, I want 3 wins out of 5 games. This is a little bit more complicated. So you start off looking at this pretty simply. Okay, I want 3 wins. 1, 2, 3. And then that means 2 losses. And then maybe like this. And then right about here is where I get bored. Because then I realize, oh crap, I got to change my order around here, right? I got to do like 1, loss, win, and then win, loss, win. I'm getting bored. I'm at 5 and I'm like tired. So you might want to wonder how many of these are there. Well, let's actually use the binomial formula. So here, you want to have 3 wins. And I want to figure out what value goes here. So I want to be able to count how many ways can I arrange 3 wins in 5 tries. So I know I'm going to have 3 wins, so 0.1 to the third. And I know I'm going to have 2 losses, so 0.9 squared. What I need to figure out is this, and I'm going to use that NCR stuff to do it. So I'm going to use 5, but I'm going to choose 3 wins this time. So I'm going to have 5 factorial over 3 factorial times 5 minus 3 factorial. So earlier in the one I did it kind of poorly because I just did the subtraction, but I want you to see where all this comes from. So if we write this out and simplify, that'll be 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1 times, let's use parentheses for this because that's looking messy, 2 times 1. So I can get rid of a bunch of these. So let's just get rid of these 2. And I'll get rid of the 3's. And then I'll just do some multiplying. So 5 times 4, that'll give me 20 over 2 times 1, which is just 2. So this ends up being 10. So that tells me that the value that goes here is 10. And that's the number of ways this can happen. Pull out your handy dandy handheld calculator because I totally forgot to calculate this beforehand. I'm an expert at that. This is actually kind of small. And it would have been a lot smaller if you missed that 10. So a couple things about this. Why does this work the way it does? You might ask yourself that. So what this is doing is it's accounting for the fact that every win looks the same. So when you look at 5, this is just the number of ways to arrange 5 distinct objects. So if you think about it this way, that numerator is coming from how many ways could I arrange this, and then dividing by the fact that all 3 of my wins look the same and all 2 of my losses look the same. So what do I mean? So if you have 5 books that all look different, and you want to arrange them on a bookshelf and see how many different ways you can arrange them. When you go to place the first book, you have 5 choices. When you go to place the second book, you have 4 choices because you've used one book, and then 3 choices, and then 2 choices, and then 1. So this is how many ways you could arrange 5 distinct objects. But the problem is here, things aren't distinct. When I say distinct, I mean they're all different. Your wins look the same and your losses look the same. So when you look over here at this 3, it comes from the fact that all 3 of my wins look the same. And the 2 comes from the fact that both my losses look the same. You know what I mean? If you're having trouble with this, if I wrote out win 1, win 2, win 3, loss 4, loss 5, this would be like they were in order, but that's going to be the same thing as if I switched up the location of my losses. So let's say my loss 5 was in this position, my loss 4 was in that position. Position 4 has a 5 in it and 5 has a 4 in it. But we don't keep track of position, we're just keeping track of how many wins and how many losses because I'm counting my successes as my number of wins. That's what my random variable x is. So that these two look the same, even though their positions might not be the same. And that's why I need this division here, because it takes care of the fact that they look the same. Trippy, right? All right. You win at least one game. This sounds hard. Why is this hard? Well, to win at least one game, that means I have to be greater than or equal to 1, which means I need the probability that I got 1 win or I got, 2 wins. Let's see if I can erase that and have it look okay. Yes! Eraser doesn't always work great. Or 3 wins, or 4 wins. I'm trying to make this fit. It'll be okay. Notice it's getting smaller. Or 5 wins. 5. Scary. Okay, so you notice I did 3 earlier, and you saw that took me a whole page to do. So 4 is going to be longer. 5 is going to be about the same length. And so is 2. Crap. This is horrible. Ugh. Yuck. So, remember a long time ago, as in last week, I told you sometimes when it's hard to do something, try doing not it. So I want you to ask yourself, what's not in here? Let's instead do the complement. Who's not in here? So I've got 1, 2, 3, 4, 5. Who's not in there? If I have to win at least one, the only thing that's not in here is the probability that I win none of them. Which would be all losses, which should be pretty easy. All losses is just 0.9 to the 5th, which we did earlier, but I forgot what it is. So I'm going to have to calculate it and then do 1 minus it. I should have put this down here. If you remember, this was our probability from our first part of this example. P.S. That's also a tricky thing that your textbook likes to do. Use values from earlier a second time. So don't be afraid to look back and be like, hey, did I already calculate this? Can I use it again? Heck yeah. So be careful. When it comes to at leasts, especially, anytime I see this, I always try to do, well, what's not in there? So if it was something like, hey, I want at least 3 wins, I don't want to do 3, 4, 5 and add them together. Instead, I'll do who's not in here. Well, if you're not at least 3, you're the stuff less than 3. But be careful, less than 3 here, because we're discrete and whole, means you're 2 or smaller. That's a funky X. Oh, because I was trying to make a 2 at first. My brain works. Yeah. So here I'd have to do 2 and 1, because I already have 0 right there that I could use. Good times. Or not. Depends on how you like doing these. All right, let's go back to the bank example. So if you do the same thing with the bank example, you'll have to go through and do all the combinations to actually figure out what all of these are. So 8 choose 3, 8 choose 0, 8 choose 2, 1, 4, 5, 6, 7, all of them. This is about where I want Minitab, because Minitab does this in like 3 clicks. Well, it's actually, I think, 2. Now I'm thinking too deep about this. So these are the number of ways it can occur. Then you calculate all the probabilities and multiply them together, and you get the following distribution. Oh, I forgot that this was going to be here. You've already seen me do this multiple times. Don't let the X fool you. That's just your number of times that you had a success. That's down here. That's from your random variable. You saw me do this already, so I don't know how important it is for me to talk about it again. Watch out for Q. So if you had X wins, then you must have N minus X failures or losses. Yep. because n is your number of trials, and they must add up to be n. And then this part right here, that was my NCX, which I keep accidentally calling NCR because that's what your calculator calls it at. It's the number of ways you can arrange X wins in N tries. All right, let's use the binomial formula for the bank. So we're going to find the probability. I had 3 customers that said they like the Saturday morning opening out of 8. So here I'm choosing 3 out of 8. So the first thing I noted is that, hey, our little p, our probability of success, is 0.8, and then I'm going to use the combinations to calculate this. So I wrote it out typing-wise, in case you hate my handwriting this time. So notice here's me doing the combination of 8, choose 3, and then here's my 3 successes, and then my 5 failures, because it's 8 minus 3 makes 5. It's got a total up to everything. You multiply those out. I'm rounding like the devil a little bit here, just to make it easier. You're gonna have to do this a couple times in your homework where they'll say, hey, I want 3 places. Sometimes they'll want 4, sometimes they'll want 5. Just be careful, wait to round until the end. Don't calculate this guy and then round, and then calculate this guy and then round, and then this you'll never have to round, so I shouldn't say that. And then multiply them together, because that will definitely make you have a lot more error and possibly get marked wrong, even though all of your work is right leading up to it. So just be a little careful. If you can, try not to round or use more decimal places than you think you're going to need so that you don't accidentally get marked wrong when you would have done things that I would have marked right if you had handed your homework in by hand. Anyway. So that's where this value in particular is coming from in our distribution, and then you can imagine similarly doing the rest of them on here. Good times. I'm going to show you how to do this one on Minitab, and it's so much easier. It's just heart. I don't know. Ew, that's an ugly heart. All right. If you want, at the back of our textbook, there is a cumulative binomial probability table. This only works well if you already know your population proportion P, and it falls within the set number of values that appear on the table. So be careful. There's lots of these tables on the internets. They're huge. I really suggest that if you're going to be doing this, you actually use a bit of technology, either your calculator or a Minitab to do these, because it is much faster than relying on the table to do so. So in particular, the table is going to be different for every single value of n, every single little p, and then every single value you're interested in. So here's the code key behind this also, if you want to use that. So if I'm looking for less than or equal to 3 successes or 3 or less successes in a thing that has 10 trials, or if you want to think of this as 3 or fewer, I guess, and the probability of success is 35%, this is the value you would get. These are a little weird and huge. If you'd like to use the one from your textbook, again, it's in the back tables section. Alrighty, so things to be careful about. I've already mentioned this, but it's worth doing again. If I want to find a value in between 2, I can also use the cumulative table, but the table only will do less than or equal to's. So if you want to do 2, you got to take less than or equal to and subtract less than 1, so that the thing that's in between them is 2 that you're missing. It's a little trippy. So to use the table to do this, we're going to look at an airline where we're looking at the possibility of no first class tickets being taken, and we're looking at 10 first class tickets because most flights have very few first class tickets. And we want to know the probability that exactly 2 people will be no-shows. Knowing that the probability of getting a no-show is 0.08. So looking at the table, here's the difference between 1 and 2. So keep in mind, remember when you're looking at this, this is doing x is less than or equal to the value being displayed, not equal to. So you can't just look up 2. It's doing stuff to the left of it or stuff less than it. So this value is the top one for the one less than or equal to 2, and this is the one for less than or equal to 1. So to find the difference of the 2, you'll do the larger one minus the smaller one, and you'll get the value in between them to figure out what 2 is. Again, I don't recommend this because we're going to see how to do this on Minitab, and it's much easier, I think, than using the tables. But some people like the tables, so to each their own. If you like the tables, no judgment. Although it feels like I just said I would judge you. Yikes. All right. So to recap and relate back to the thing we did earlier, when you want to find the mean of the binomial distribution, it's just n times p. Now this shouldn't be a bit of a shocker. If you have a 1 in 10 chance of picking out somebody who's left-handed and you select 10 people, you should expect to have on average one person who's left-handed in that group. It's just the number of tries times the probability of success. Similarly, if I have an 80% chance of winning, if I play 10 times, I should win 8 times. You just multiply them together. Now, this is the one that might scare you a little, but it makes sense when you think about it. The spread is the number of times I play, probability of winning, probability of losing, since I could have both happen. And then the square root comes from the fact that things get too big if you don't do the square root for a standard deviation. It's kind of fun. When we look at the normal distribution next week, you'll see how this also relates back to the normal, and it's actually kind of cool how they all interact with each other. Here's a look at the bank examples, spread, and standard deviation. So we went through and we actually calculated this part a couple slides ago. I think it was 8 slides ago. And you can take and actually calculate this by hand. So doing stuff we did from the very beginning of slides where we calculated probability distributions, mean, and standard deviations. So we multiply them all together, and then we do their difference from the mean, and then we square them, and then we multiply by probability. We add all those up and take the square root. You'll get this. So that's the values that we would do from the tables. However, if you make note that this is a binomial, you can just do NP and get 6.4 and NPQ and get this stuff, which is the same spread. It's kind of fun. That circle looks bad. Let's use an underline. So this binomial note is really just to make your life easier. It's much faster to do the calculation doing the square root of n times p times q than doing the entire table if all you need is the spread. So my pro tip for you is, when in doubt, use these guys if it's binomial, because they are 100% faster than doing the entire table if you're not going to need the table. Just saying. All right. Let's look at a last example. So this is an example from quality testing, or also known as quality improvement. So we're looking at a supplier, and they call the purchase 3,000 components. About 5% of all defects means that we consider this a bad shipment. About 10% will mean, or sorry, it's a good shipment, and 10% will be a bad shipment. So basically, there's a situation here where if I have a certain number of defects, I'm good. You know, my supplier won't be pissed at me. And then I've got this scenario where, they're going to be very angry and be like, what the heck? Why you got so many defects, you know? So let's look at a sampling pan for this. So if I'm going to ship 20 items, the number of defects needs to be less than or equal to 1 in order for it to be accepted. In order for the shipment to be rejected, you will have more than one defect. So where I get less than or equal to 1 from as being a good shipment is if you do 5% of 20, it's 1. That's acceptable, but bigger than that is going to be too high. It's going to be too big of a percentage. So I'm really only using the upper defect rate to come up with this. Could you use the lower for that? Yeah, you could, because it would be 2, because 10% of 20 is 2, and then we'd be looking at less than 2 would be acceptable, so less or equal to 1. Same idea. These actually come out the same. Good times. So we want to have a high probability of good shipments and a low probability of bad. I think that's pretty normal for what your expectations should be as somebody who's a supplier. Let's take a look at the binomial table. So here I'm just doing less than or equal to 1 because that's my probability of good shipments, knowing that my number of items I'm shipping is 20 and my probability of success is 5%. So this is my resulting value. So I should have good shipments about 73.58% of the time. That's not very good. Oh, I forgot that I did that at stages. Oops. Probability of accepting a good shipment. Good times. All right, so what's the probability that something bad happens, or aka they accept a bad shipment? So we want to look at less than or equal to 1 with a probability of 10% because that's my defect rate, if you remember that from earlier. So we want to be looking at this column for n equals 20 because I'm looking at shipping 20 items out of the 3,000 in a pack, and about 39.17% of the time they will accept a bad shipment. This is not a good thing. This is what we would call an error in quality improvement. All right, so probability of accepting a good shipment will be 73.58%. The probability that they accept a bad shipment is 39.17%. Uh-oh. So do you like this sampling plan? It's probably not very good in my opinion. You have quite a high rate of having a bad item being accepted or a bad shipping plan being accepted here versus something good happened. To me, this is an unacceptable level of error.